start. Okay. So, last week, conceptual and logical design. This week, a little bit about how you go about converting those, your logical design into a physical database design. Okay, so, yep, basically from logical to physical. The main bit of it is about the process of normalization, which is part of the process of converting from logical to physical design. Also going to touch on another number of other topics exceedingly briefly, indexes, and also I added a slide or two on standards this morning in the last 20 minutes, just because I thought it might be relevant. But we're going to go into some of these things, indexes and standards, a bit more later in the module. So basically, it's mostly about normalization. So what does the move from your logical design, which should, as I explained last week, should fully specify your database model, but without reference to any particular software. So it's a sort of, it's a model that's separate from how it's actually implemented in a database management system. So you have to actually, you take that logical model and now have to actually implement it in a relational database. So the basic process is kind of this, six stages. Entities are implemented as tables. It may be that an entity maps onto one table, or it may be that an entity maps onto more than one table. So it's not necessarily a one-to-one mapping or correspondence between entities and tables. Often it is, but it's not always, and we'll see in a minute. And to a certain extent, that's what normalization is about. Attributes have to be implemented as data types. Domains, sets of valid values within a column are implemented on columns. Basically, domains are further constraints on data types, which are also defined on columns. We go through the process of normalizing the tables. So tables exist here, implemented as tables, number 1 and number 4, and I wasn't quite sure whether to put normalization with the tables or not. Often it's the case is you come up with an initial set of tables and then you sort of redefine them, reevaluate them as the process of through the process of normalization. So it's not just a linear process, it's an iterative process. You're learning as you go about the design. Constraints are implemented on columns, including primary keys and any other constraints. So, for example, in a spatial database, there may be topological constraints. So these polygons can't overlap, for example, that kind of constraint. And we may build indexes. So that's the basic process, or the tasks that need to be undertaken. And as I say, they may not be actually undertaken 1 to 6. They may be, you may jump forwards and backwards between them. And indeed, I will in the following slides. They won't be numbered stages 1 to 6. They'll sort of jump about a little bit. Data types. This should be, it's one of the sort of, hopefully, an incredibly self-evident fact, but people often don't do this, which is to use the correct data type for the type of data that you're using. And that maybe seems just so obvious that it doesn't need saying, but there are many, many databases out there which don't use the right data type or database data type for the type of data being stored. One of the particular area where this fails is date and time. It is quite common to find people storing date and time as text strings rather than specialist date time data types. Why do they do this? Well, it's quick and easy, and if you're not searching on dates a great deal, it maybe doesn't impact the day-to-day usage of your database. So you could say that there are practical reasons for not bothering with date and time fields. But it has basically two types of problems doing this. One of them is that a character field could store any data. So you're trying to store a date, like the 26th of February 1963, in a text field. Well, anybody could enter any value into that field whatsoever. It doesn't have to be a true date in any way. The dates can be formatted in different ways, leading to inconsistency across your data type. So while it can be done like that, it's not a good idea. The other major disadvantage is that you can't use any of the time functions that are available in the database for calculating things like, I've got a date and I want to know how many days ago that was from today, for example. So there are all these data types to do with time that allow us to do things like that. To truncate, change the format of the date, time field, things like that. And we'll have a lecture on time later in a few weeks' time. So there's both disadvantages. So you've got disadvantages because you've got flexibility in what can be stored in there, lack of control over what can be stored in the field, and also you're losing a lot of potential functionality through the time functions. The one time that I would say it probably is okay to store dates and times as a non-date time field is the situation where you have a year only. 1976, 1935, something like that. To me, that can be pretty much treated like an integer. That you don't gain much benefit over the time functions, the date functions operating on years. Years are generally can be treated as integers. However, generally though, because there are cases where you can't treat years as integers, and you may want to actually store them as date-time functions. I don't know whether there are any available, but there are a number of different calendars in operation through the world in the present day and in the past. So if you're dealing with sort of historical data that goes back pre-19th century, you may actually be operating on a different calendar. I always get them muddled up. There's the Gregorian and the Julian calendar, and I can never remember what we're presently on. Is it the Julian calendar or the Gregorian? So there's alternate calendars. So if you've got dates captured with different calendars and things, you may well want to use the time functions to convert between these alternatives. Anyway, so try and use the correct database type. Well, what is the correct database type to use? Well, it's the type, the data type that it encompasses, that allows you to store the range of data values in that field, but which minimizes the disk storage. You take the smallest thing that does the job. And this is not necessarily, there are a few tricks and approaches to dealing with this. Well, first of all, we'll maybe look at we've got these, so here's the numeric data types in the table at the bottom, the numeric data types from Postgres. And we can see we've got a whole choice of these. And we've mentioned these in the earlier lectures. So we've got a small integer, which takes 2 bytes of disk space and allows us to store numbers from minus 32,768 up to plus 32,767. If we've got larger numbers, integer numbers, we might use an integer data type, but that involves twice as much storage. Clearly, if our numbers are only going to be in this range, we want to store it as a small int. We're using half the disk space. It's going to have a knock-on effect on the speed of our database. There are a few tricks, as I say, I've got a couple up here, that can basically mean that you can get a larger number into a smaller number of bytes than the standard data types provide. So, for example, if you have no negative values, so if all your values are 0 or above, what you can do is apply what's called a signed integer. So these are normal integers, but you can also sort of tweak them and call to be signed integers. And a signed integer, what basically happens is all the negative range gets pushed over. You've got enough bytes, because you're not storing negative numbers, you've got enough bytes to add the negative values to the positive values, so you can go up to about 64,000 odd plus values if you used a signed small integer rather than an unsigned small integer rather than I think that's an error on here, so then use unsigned numeric type. So that should be unsigned, not signed, because you're removing the sign, the negative sign, the negation sign, which increases your ability to store larger numbers. So that's one way to go up to 64,000. Say if you have 50,000 records, you could use an unsigned small integer as your unique identifier. Here's another trick that's used quite a bit, so I've come across this one quite a lot, is if you've got data that's stored to a certain number of decimal places, say 2 decimal places, all your data goes to 2 decimal places, then rather than storing the data in a decimal data type or a real data type with 4 bytes, say we stored it as say we've got 2 decimal points, then we could store it as a real number numeric data type which takes up 4 bytes on disk. And that is giving us 6 decimal digits of precision, so we've got 4 extra decimal significant figures after the decimal point that we don't need. So it's more efficient. We can store exactly the same data more efficiently if we multiply all the values by 10 to the power x, where x is the number of decimal places, to give us an integer. So, for example, say we've got a value of 20.12, 2 decimal places, so we can multiply by that by 10 to the power 2, which is 100. Yeah, 100. And that gives us 2012. And we store that in a 2-byte small integer data type. We've halved the data storage on disk by turning our decimal values into integer. Now that's great for storage, but you've got to make sure that the users understand that that's what you've done to the data and the data has been transformed. This is done, an example of this is the WorldClim global climate data set, which gives you number of climate variables in raster format for the whole globe. And they supply it, I think it's to 1 decimal point, and they do this multiplication to integer so that the grids that you're downloading, the grid files that you're downloading are a lot smaller than they would be if they were decimal numbers. If you're doing large, high resolution, it's a sort of global data set that goes down to the resolution of about 1 arc second, which is roughly 30 meters on the ground surface at the equator. That's a huge amount of data if you were wanting to download the entire data set for the globe. So it really makes a difference when you're dealing with these large data sets to use these tricks to reduce data volume. Object names. Now, what do I mean by objects? Objects in Postgres are any of the things that you create in Postgres. So a table would be an object, a schema would be an object that contains containers. Index is an object. All these things that you manipulate in the pgadmin 3 window you can think of as objects. And there's 2 types of things to think about when you're naming your database objects. One is that there are physical limits to the system that the system imposes. And in Postgres, for example, the table name can only have 63 characters long, I believe. When you're checking these figures online, like I was a few days ago, you hope you get the right result, but as I say, software keeps changing, so it may in fact be different now than it was from the figures that I've got, but always bear that in mind. There are certain rules, table name 63 characters max. I'm pretty certain that there is a rule that says no spaces in table names as well, or indeed any object name in Postgres. There may well be other reserved characters. You might not be able to use a star. You might not be able to use a / as part of a table name. So there's system constraints on what you can name objects, but there's also conventions that you should also consider applying to naming your objects. And we've touched on this before. So one is use meaningful names that are descriptive. Don't call it table 1, table 2, table 3, table 4. I know that's an extreme example, but it's not very sensible. Call it student, call it staff, call them address. So give them meaningful names. Generally good idea to use singular, not plural. So it's address, not addresses. Student, not students. It's not, there's no, nobody's going to stop you calling it students, but it's generally done that things are kept singular. It's one less character to type. Every character more that you type in your life is one bit more of your life wasted. And then there's the styles of naming. Now again, these are just rules of thumb. Everybody does it slightly differently, but there are general approaches that more people take than other people. So particularly consistent capitalization of use of underscores. And you'll discover, of course, in the practical materials and things that I don't follow all these conventions all the time. I slap myself on the wrist, but if I was working in a large group environment, particularly where you're working as a team, it's really important that you follow the sort of convention much more closely. It makes everything easier for everyone. So for example, on the Postgres site, they suggest using Pascal case for table names. Oh, I've got a space in there, that's terrible. So I shouldn't have a space in that, that's awful. So get rid of that space. So Pascal case is each word in your name is capitalized. So the first one is capitalized, Pascal, capital P, case, capital C. Get rid of that space. That's direly wrong. Column names suggested they use what's called camel case, presumably because it looks like a camel, with a small c for the first word. Subsequent words begin with a capital C. Also, they tend to use underscores to separate the words that are concatenated together to make a table name or the function name when it comes to functions. So it tends to be my underscore function for function names. Not function mains, but some function names. And at the bottom here, never use spaces ever. Now I have that. I do this principle, I try to, even for Word files and things like that, which are generally in Microsoft supported and generally across most computer systems sorted. But there are still problems with have spaces in file names. You may need to end up quoting them where you wouldn't, put quotes around them where you wouldn't if they were a continuous string of names. And many bits of software simply don't like spaces, particularly things that have a longer development history like Postgres. So Postgres goes back into the 1980s, where spaces in file names were a total no-no. Indeed, if you remember the days of DOS and old DOS days, when you only had 8 characters for a file name and then dot and then 3 for the extension. So never use spaces ever for table names, disaster, broke my own roll there, or for column names or for function names or for any object system names. And I would say do that as a principle throughout this module and throughout the rest of your life. I mean, it'll work. The thing is, it'll work 90% of the time. But then it won't, and you'll spend days having hell, and then you'll have to work out that the last months of work, which is full of file names that have spaces in, has to be gone through and every space removed because one bit of software that you're using doesn't take spaces. Anyway, so never use spaces ever. Is that clear? Right. All right. Here are diagrams to tables. So how do we turn our diagrams into tables? It's relatively straightforward. After all, your logical design should pretty fully specify your database model. So it's a relatively mechanistic process. However, there are still design decisions to, it's not a completely mechanistic thing, or it doesn't have to be. So here's a situation. Here's our ER diagram. It's to do, well, I don't know what it's to do with. It's people and passports. So maybe it's a border control system monitoring people coming through across the border. So one person has between 0 and n passports in the logic of the thing. So we're trying to find people coming through on different passports, perhaps. We've got a target, a criminal gang or something, and they use different passports to come through border control, whatever. So each person has 1 to n, 0 to n passports. This is our entity relationship diagram. Well, this is very straightforward. This is simply a foreign key situation. So we can convert each of these entities into one table. We've got a person, where the person ID is our primary key for our person table. We've got the surname, and then we've got a passport table with a passport number, place of birth. Oh dear, Varkar 100, terrible. That should be a date, obviously. That's place of birth, sorry, place of birth, that's fine. And a date of birth is a date field. And we have the passport number as a foreign key in the person table. Very straightforward. One person can have between 0 and n passport records associated with them. The passport number must be is a foreign key in person, because the passport must exist for a person to have been spotted with passport. Now, n to m relationships are slightly more complicated, not a great deal. So this is a situation where we've got several passports are being used by several people. Okay, it's perhaps not a very, so perhaps we've got twins or something like that. That they wasn't exactly, could have perhaps thought through the scenario a bit better, but it's the principles that count. Okay, so we've got, in this case, we've got a person using a passport on a particular date. This person was spotted with this passport on a particular date. So this is a slightly more complicated situation. Now, what you do or how you go about converting this is one of these design decisions in the conversion between the logical and the physical model, or could be, because which depends on whether whether you need both a person and a passport for the passport to be used. Okay, so obviously a person needs a passport, but you might know that a passport has been used, but you don't know the person who's used it. Okay, so if you've got that situation where you may have a passport used record, but this could be 0 here. So it depends whether this is an obligate relationship or not. So if this could be a 0, so you could have a passport with a used date, or does it have to be a 1, in which case you have to have a person, a passport, and a use. Okay, so how you deal with it differs depending on the circumstances. So if you need both a person and a passport, then what you do is you implement a third new table, passport use, with a composite primary key composed of the foreign keys of person and passport. Okay, so here we've got person, person ID, surname, passport, passport number, date of birth, place of birth, date of birth on the passport. And here we've got the usage, and we have the person ID and the passport number, foreign keys from passport and person, and together they make the primary key of the new table, because you must have a person and a passport for a passport use situation. But if it's just dependent on passport, so you can have passport and a use but don't necessarily have a person associated with it, then again you implement it as a new table, but you need to, this new table needs to have a primary, have its own primary key, because you can no longer define a primary key both on passport number and person number. Okay, so you can't, you can no longer define a primary key on that. I must say, actually, now I'm thinking about this, of course, what happens if a person, you might not, on the previous example, this only allows a person and a passport. This situation only allows a person and a passport to use a passport once, so it's probably not a very good design now I'm thinking about it. And indeed, in this case, if you wanted more than one usage of the passport, then you couldn't use person ID and passport ID as the primary key, because you'd need multiple records with both a person number and a primary key. So I'm thinking that this design is actually better for both situations. But the point being is that you can implement the same logical model slightly differently as a in the physical model. And that depends to a certain degree on how well and how closely you've defined your logical model. So if we actually had figures instead of M's and M's there, we might actually, if we actually had zeros and ones and a bit more detail in our logical model, perhaps what I'm sort of slowly crawling my way towards is the fact that the logical model is perhaps not as specific as it should have been to fully define the database system in this case. An end-to-end relationship in itself is not sufficient to define how best to implement it as a physical model, if that's relatively clear. Anyway, so the alternative one here is we just put a unique ID for passport use and use that as the primary key. So we create a unique primary key field for the passport use, and then we have the person ID and the passport number as foreign keys with a non-null restraint on passport number, because you must have a passport number to have had a usage of a passport. You might not have a person. So that's basically end-to-end relationships you decompose into a third table, a connecting table. Column constraints. Okay, we've met unique, we know unique. All values in a column are the same. Must be unique, sorry, must be unique. This can be imposed on any column. It doesn't have to be a primary key column. Any column can have a unique constraint put on it. Not null. Similarly, null, not null. Whether it can include nulls or not nulls. Any column can have a null or not null constraint put on it. Doesn't have to be a primary and foreign key. As we see, we've met primary keys. Primary keys important, and foreign keys important in maintaining database integrity. And we know that the primary key is a combination of a unique and a not null constraint on a column. And a foreign key, if we remember, uses the references word to look up values in the foreign table with the matching key. So it references a table, a column of a table. The next thing we're going to look at, or a new thing, is the check constraint. And the check constraint is basically how you set domains, or one of the way, or the main way in which Postgres implements domains, and indeed relational databases in general. Domains being the valid range of valid values in a column. So let's have a look at setting check constraints. Range of valid values in a field. So here's a check constraint example on a single column in our create table function. It's a products table. There is something being produced. Product number integer, product name text, and a price field, numeric price field. And for some reason, well, not for any reason, the price can't be 0. The price has to be more than 0. You can't sell anything for negative money or for give it away in this database. So what we have is a check constraint on the price field, and we check that the price, probably should be a capital P rather than a small p, the price is greater than 0. So any values that are 0, 0 or negative will be rejected when they're entered into the database. So that's a simple check constraint on a numeric range. You can also put constraints on more than one column, a check constraint, or through use the constraint keyword separate from individual fields to set a constraint across multiple fields. So here we've now got a second constraint. So we've now got, we've got 3 constraints in this table, or products table. So we've now got a new field called discount price, and I've got it the wrong way round. I've had a filthy cold all week and just my general incompetence. But anyway, so in this case, we've got the original check, the price is greater than 0. The discount price, we've got that the discount price must be greater. Oh, sorry, check. Oh, dear me. Discount price, this should be check. Price is greater than, that should be discount price, not 0. Sorry. So that should be discount price, numeric, check, discount price, greater than price. Dear me. I will update these, stick them up, the updated file. That's the greater, yeah. Okay, so this should be discount price greater than 0. So both these should be greater than 0. And then in the third one, sorry, I'm just still suffering from this cold, which awful. So price check is greater than 0. Discount price should be discount price greater than 0. And then we have this third individual constraint, which is the called valid discount, which is the checking that the price is greater than the discount price. Yeah. Okay, so that's a constraint on. So we've got 3 constraints on this table, one of which is a constraint on 2 of the previous fields. Lookup list constraints. Okay, so this is where you've got a list of items, something like a list of countries, a list of postcodes, a list of anything, so that are valid entries into a field. And this is, again, an example of where you've got a choice between how you implement a lookup list constraint in your database system, in your physical implementation. There are 3 options that we've got here for doing this, 3 ways of doing the same thing. One is put a constraint on the column. Another alternative is to define what's called a domain object, which is a constraint imposed on a data type and used as a data type. And the third thing is to impose a foreign key constraint. So our example comes from the same as examples data set from last week. Only allow valid continent names. So if you remember this from last week, here's how we did it with a check constraint last week. If you remember, we didn't meet check constraint last week. So here's our country table, and at the end we've got a constraint called country continent check, and it checks that the continent equals Asia, or the continent equals Europe, or North America. Is a long or set of or commands. Now that's all right if you've got 7 continents, but imagine if you had 20,000 postcodes. Not exactly a very sensible approach to it, but fine for small amounts of limited numbers of entries. Also notice here that we've got the constraint, they've used the constraint approach with the check afterwards, separate from the definition of the consonant field. And I think they've just done, this is done like this simply for readability. I think this check constraint could quite happily have been embedded in there after the consonant, the not null constraint there, could be stuck there, but it's just neater to see all the columns presented individually and then to have this rather large and bulbous check constraint at the end rather than embedded within the field name definitions. So it's just, I think, simply a readability issue here. And it may be just personal choice. So that's the check constraint. Here's the second approach, and that is to define what's called a domain object in Postgres. So what a domain object is just a data type with some additional constraints set upon it. So we're going to create a domain object here called consonant name as a text data type. So it's a text data type, but it has associated with it a check constraint. So it's a text, it's a data, we're creating a new data type, effectively, we're calling consonant name. That is a text one, but also has an additional check constraint. So, and the value is in this array of values. An array is just a list, another word for a list. So in that array, Asia, Europe, North America. Okay. And then when we define our table, we can see that the consonant field is no longer a text field per se. It's defined using the consonant name domain that we've defined here. Okay, so we're defining the data, rather than saying it's a text data type, we're saying it's a domain which includes the definition of a text with additional constraints. Okay, that's another approach. The third approach is a lookup table through a foreign key. Okay, so in this case we create our consonant table. We create a table called consonant. So in this case we've actually created a new table called consonant. Remember, it was country, which we want country to look up, country consonant field to look up. We insert into it our values, that should be 2 and 3, of course, get more errors. So Asia, Europe, North America. And then when we create our table country, we have set a foreign key. So consonant is an integer which references, so in this case we're storing the ID rather than the name. Now why do we do that? Is because if we store the name, if we store the consonant as an integer value, so the row value, sorry, that one should be 2 for Europe, 3 for North America. I've got to go back and correct these for you. 1 and 2 and 2. You're only storing the amount of bytes needed to look up an integer rather than the number of bytes here to look up the name. Okay, so it's using less values. Okay. So looking up integers is quicker and less storage volume intensive than looking up strings. So the consonant is an integer, the consonant ID value, which references consonant ID. That means that we can't insert a consonant into our table unless it matches, the ID matches one of the rows in the table. Okay. Oh, a new continent has been discovered, the continent of Mu, also known as Lemuria. Yeah, it was there all along and we never knew where it was. I've got a thing for legendary continents. It's like Atlantis, Mu. It's one of these legendary, advanced civilization places or whatever, allegedly in the Atlantic. Okay, so Mu has been discovered. So let's just